Okay, so today we're going to continue, and today we're going to finish the topic of fine volume discretization. And I want to start with the procedure for, actually not only the procedure, but I want to show you how to assemble the matrix of the implicit formulation of the fine volume method. Yesterday, what we have covered was at the end of the lecture, we've been discussing whether it is possible to do the time stepping using the explicit fine volume scheme, and the answer is yes, it is possible. So let's try to do something that is probably more reasonable and more popular to be done to formulate the implicit formulation of the fine volume method for the advection diffusion equation, for the scalar equation, but we'll do that for the case with the Upwind discretization scheme. So, well, first, advection diffusion, Upwind implicit. All right, so let me draw some portion of the grid. Let's assume that's the cell that we are discretizing with omega v. And as stated yesterday, we know already that the formulation should look like integral over gamma of the cell. And what was it? It was like the velocity times the variable at the face, times the surface area of the face. Did we have something more? Yeah, right. Unit normal vector at the face. Well, plus or minus the diffusive term, gamma v.
But there's no area. There's no area.
Yes, since you're integrating the
Yeah, right. Yeah, right. I have mixed two different things. Well, let it be temperature. Well, plus or minus, I don't remember, and I haven't got the notes today.
And it's not, you can't have temperature in U. It's either both U or both T. I think.
not exactly, because U can be like energy and.
No, really, yeah. We want to write the equation for U. So, well, please check in the notes whether. Yeah. So after discretization, what we come up with is the sum of all faces, unit normal vector at the face, times velocity at the face, times U at the face, times the surface area of the face, minus sum of the faces, well, the unit normal vector, not really lambda f that we discussed yesterday, the harmonic average if there is variable lambda field, times du dn evaluated at the face times surface area of the face equals 0, right? Good. Then if we want to if we want to define the implicit scheme and do the upwind, what we need to do is to split this term into this formulation with maximum and minimum. And well, how do we do that? We need to make sure that if we've got the unit normal vector and the velocity at the face is somehow oriented outwards of the cell, then what needs to be done is, let me write that and let's check. Times U at a phase. If we are talking about upwind discretization, then it means that if the flow goes out of the cell, then we need to use our value, which would be, let's call it, well, maybe a stupid notation, UI, okay? I should have probably two different indices, like the upper index and lower index, but let's call our value UI. And then AF sum over faces plus sum over faces min 0 unit normal vector times velocity at the face times, and let's see if it goes inward, then it's got minus negative sign, then minimum selects this part, and we should take the value from the neighboring cell, right? U
Maybe an F from neighboring cell, neighboring space, neighboring space.
I need to denote two things, actually, because this needs to be the value from the neighboring cell, but also indexed by the faces. Do you get it? Like UI is certainly my value in my cell, but the neighboring needs to be additionally specified because we might have, in this case, 3 different neighboring cells, and we need to choose one of them. So this would be that times AF. This one is a bit simpler, minus sum over faces.
And why do we have UNF?
Well, because N should denote, in this case, the neighboring cell, the value in the neighboring cell. Well, but you have got 3 neighbors, so you need to know which neighbor. And if we've got the sum that loops over faces, the local faces of our cell, then when we need to know whether we want to take the value of that neighbor, or that neighbor.
Okay, and F means on the face.
F, yeah, like F specifies.
Like which neighbor it is.
Exactly. F loops, in this case, from 1 to 3, loops over all local faces. And then this specifies is like it's your neighbor adjacent to which of the local faces. Okay? Let me assume, for the sake of simplicity, lambda is constant. If it's not, we already know what to do with that. then times u neighbor through the given phase minus ui divided by, well, distance between what? Distance to the neighboring centroid times AF equals 0, right? Nice. So can we already discretize that, or what kind of problems do we have with this formulation?
It's non-linear.
Well, is it?
Like,
I mean, yeah, if you treat that, it's clearly nonlinear because it cuts off something.
yeah, but if we know the velocity, it's linear.
Yes, if we know the velocity, then it's linear. Okay, good. So that's right. If you're dealing with the pure scalar equation, then the velocity is already defined. You have already solved for velocity. So there is no problem like exploiting this knowledge for each of the cells and just apply this formula to assemble the matrix. What are your unknowns? Clearly, the unknowns in the matrix are this one, the neighboring values. So again, this, that. So what you need to do is you need to gather all the terms in a way that what you want to have is ui times some coefficient plus, well, you would have the sum of the phases, so you would have 3 different coefficients times u and f equals 0, right? Let me gather that. So what would we have here? Certainly sum of the phases max 0 and f times vf. That's already that part minus, or actually plus, sum of the phases, and we need to take this part, which would be lambda. Minus gives the plus sign, so lambda divided by the neighbor f. Actually, I forgot AF, but it's the same sum, so we can simplify that. Well, a yet additional bracket if you wish, so that it's clear where the sum goes. Okay, and here, what have we got here? We've got sum of the phases, minimum 0, unit normal vector times VF times AF minus, or let's do the same, minus lambda divided by D and F and, no, sorry, AF. Right? Looks good?
Isn't there an AF missing? I know it's okay. I did so
Here?
the brackets
And here, yeah.
inside.
Mm-hmm. Okay, so right now what we've come up with is the Upwind scheme, which is implicit. So once you solve it, once you discretize that and you solve, you come up, if VF is given, and it's not constant in space, but is already solved, then you will end up with a system of linear equations. What will be the properties of the matrix?
Triangular?
No.
Like it will be sparse.
It will be sparse, yes, that's already something. How many entries can you expect in one row?
2.
This 1 plus number of neighbors.
1 plus number of neighbors, exactly. So because what you can see from here, how many entries do you have in the matrix? 1 for me, certainly. And this sum always contributes to the coefficient in front of my value. But this sum contributes to the entries that represent neighbors. So you will have always 1 plus number of neighbors. Okay, so it's sparse. The sparsity index is like 4 divided by, well, 4 for this divided by the number of unknowns in the system. What else can we say about the matrix? It won't be symmetric, yes, and it's neither symmetric nor antisymmetric, because you could split the matrix into 2 components. One of them being symmetric, that resulting from the diffusion discretization, and the other part that would be antisymmetric, resulting from the discretization of the convective part. Yeah, can you say something more about the matrix?
It's strongly diagonal. It depends on the case.
If you apply reordering of some sort, maybe.
I don't know if it's strongly dominant. To be honest, I don't think so. Certainly the matrix for the diffusion problem is weakly diagonally dominant if you do the discretization of equations, but if you add the boundary condition, then you already fulfill the condition that at least one row is the row where the absolute value of the entry at the diagonal is greater than the other entries in that row. Well, however, the problem is well defined. Once you apply the boundary conditions, the inflow boundary condition, because we said yesterday that the outflow will result per se, then it will go. It's a well-posed problem. About the structure, if you're dealing with the unstructured meshes, you will not observe any special sparsity pattern. Like, you will not see that it's like block diagonal or something like that. You will see, because your nodes and your cells are numbered in an arbitrary order. So what you would see in this sparsity pattern is probably something, sparse, but not really. The entries are not gathered across some diagonal or something like that. One more comment is what happens if you deal with discretization of the flow problem. So so to say, the advected quantity would be velocity also. Then you've got the velocity, and you've got velocity. Or what happens if you are co-simulating to phenomena that you're updating the velocity field, then you're updating the scalar quantity transport equation, then you iterate the velocity field once again, iterate the scalar quantity, and so on and so on. What kind of problems do you deal with?
It's nonlinear.
It's nonlinear. Where does the nonlinearity come from?
From the Upwind scheme.
Yes. So you need to have the velocity to calculate coefficients to the matrix. That's the problem. How do you deal with that?
You take them from previous iteration.
Usually, yes. Like there are a couple of ways to, well, first of all, what you need to do is you need to linearize the problem to come up with constant coefficients that you will be updating from one iteration to the other. There are many, many ways to linearize the system. Probably the simplest one, and pretty often used, is simply taking the velocities from the previous iteration to calculate the coefficients in the matrix and use these coefficients to solve the problem for the new, well, not necessarily time step because it's a steady state case, but just for the new iteration. It's one of the possibilities. Sometimes you can use some extrapolation. Let's use maybe 2 previous values of velocity, and let's try to extrapolate to the new solution. Or let's do some under relaxation. I think we will be discussing things like that during our last lecture. I will want to discuss some concepts like linearization, time stepping, iterations in pseudo time, etc. But generally, yes, you need to linearize that very, very often, taking the velocity to coefficient calculation from the previous iteration. Questions?
Is there any motivation to use certain type of elements in finite volume? Like here, for example, we have a mixture of quartz and triangles, and apart from geometry of the problem, like only for numerical reasons.
Well, actually, probably only these things that I have discussed when talking about meshes. Generally, if you use quads, or even the triangles, you would like to generate mesh in a way that the segments, the line segments connecting the neighboring centroids are at the 90 degrees angle with respect to the edge, because then you have little mesh skewness and relatively small error of the discretization of, for example, the diffusive flux. Generally, quads are better when it comes to the number of unknowns that you would have in the system compared to the number of cells. So that's nice to have quads if you can have them, but there only exist fully automatic meshing algorithms for triangles, for arbitrary geometries. So, like, depends. Choose one.
Also, if we got like flow like in one direction, the structured mesh does like introduce less numeric diffusion.
Yes, that's right. If you've got flow that is flow whose direction is aligned with the grid lines, then you have little numerical diffusion. Okay, Apart from that, everything clear? Then let me go to the last topic that that covers fine volume discretization for scalar equations, and then we will be moving to Navier-Stokes, or generally. Or one more thing that I would like to ask you. I have already erased part of that, but you've got it in your notes probably. Could you like make an asterisk or something like that, because I will want to come back to that during the last lecture. If you haven't got that in the notes, let's rewrite it quickly. What was here?
Mean of 0 and normal vector times both mean
Minus lambda divided by distance.
Good.
Times the area.
yeah.
U and F equals 0, yeah?
Okay. And actually, maybe since we are denoting by the square brackets what is summated, maybe we should put it after the U and F, because it's also under summation sign.
Yeah, I know what you mean. Yes, you're right. Strictly speaking, you're right. I wanted to re-highlight what's the coefficient and what's the quantity.